Thanks very much for that introduction, and thanks for having me today. So the title of my talk is Wireless Power Transfer and RF Energy Harvesting, New Options for System Designers. So I am going to be talking about ambient RF as indicated, and I'll also be talking about some other RF power transfer schemes. Let's see. Now the reason I call it New Options for System Designers is not because I'm going to be talking very much about design, but one of the things I think is most important and interesting about wireless power is the different design options that it will create. So before I get started, I'd just like to acknowledge my graduate students and alumni. This is a Lansing Sample, who was my first PhD student. He graduated about a month after I started at UW because we'd been working together at Intel for about 5 years before that. So I thought if I could only crank out one PhD student a month, I'd really have something going. So far it's slowed down, unfortunately. Now before I get into the meat of the talk, I'll just give you a little overview of my group. I call the group Sensor Systems, and from the name you might think that that's all about inventing new sensors, and we do some of that, which is what I have labeled down here at the bottom, but we're also interested in all the other things around that that it takes, that you need to take an isolated sensor and turn it into a usable system. So that involves communicating with sensors, and most of what I'm going to be talking about today is actually about powering sensor and actuator systems. We're also interested in various applications of sensor systems, so things like ubiquitous computing, medical applications, robotics, and I'll actually talk about some of each of those. But the bulk of the talk today is going to be about our work in wireless power. Whoops, the B key. And I will unpack these acronyms as we go. These are several different systems that we've developed. So before I talk about some of the specific systems, why wireless power? I mean, in some ways it seems so obvious that you don't even need to motivate it, but it's kind of interesting to think about what are the specific benefits, partially because different applications are kind of benefiting from different things. So one of them is cord elimination. So here's a mess of cords that you see. Obviously wireless data can help eliminate quite a few cords, but it may not eliminate all of them. Of course, one way to eliminate the power cord, at least some of the time, is to use batteries. So battery elimination is another potential benefit of wireless power that works in some applications. And if you think about, well, what are the benefits of getting rid of batteries more specifically, one is your device can potentially have a perpetual lifetime. If it's getting the RF kind of live, then you may be able to eliminate the battery altogether and not worry about it dying. If you can eliminate the battery, you can reduce the size often, so sometimes we're in a volume constrained situation. And of course you can get rid of weight as well, and you'll see some applications today where the weight constraint is really the benefit of wireless power, or removing the weight constraint. Now this is one where I'm not sure I have the best description of it, but the two images you see here are images of the monolith from 2001: A Space Odyssey. So one way to think about this benefit is, imagine you have, future version of the iPhone. Here's an existing iPhone. It has quite a few connectors and buttons and things, but you can imagine if you have wireless power and wireless data, and if we sense, buttons using some kind of capacitive RF sensing technique, then you could imagine making something like a phone that's just a completely sealed monolithic box that has no ports or no features whatsoever. And actually you'll see several applications today where what you might call boundary integrity is the key benefit. So it's not just for consumer electronics, but if you start thinking about biomedical applications, that's a case where you don't want extra ports being put in your body, and we'll see some other examples of that too. Finally, here's I've got Emperor Palpatine from Star Wars helping us out here for this one. I was talking to some NASA people about the possibility of transferring power wirelessly between spacecraft, and so there the benefit is non-contact energy transfer. So if you have these spacecraft that can be sent off accidentally with small amounts of force, then the fact that you don't have to use force to make and break connections is potentially a nice benefit. So these things are all similar and related, but as we go, I'll point out when we're taking advantage of these different benefits. Now, when I think about the space of wirelessly powered systems, this is one of the ways I like to carve it up. So I have one axis, which is far field versus near field. Far field literally means further away, probably in terms of RF, more than a wavelength away. And I also have some near field work. And the far field systems tend to be smaller amounts of power, longer range. The near field systems are larger amounts of power, shorter range. And the other axis that I use is you could call it wild or planted. And that is, is this power that we deliberately transmitted with the intention of collecting again later? Or is this power that was already out there for some reason that we found and used? And that's what I'm calling wild. So each of these, we've explored several of these boxes, and these are the names of the systems that occupy each box. And as we go, I'll talk about the specifics. So one final sort of piece of introduction is, if you think about the far field systems, the thing that has made these possible is energy efficiency scaling. So if you look at this plot, not very carefully, it looks like kind of a Moore's law plot that you've probably seen many times. The horizontal axis has time in decades, but in this case, the vertical axis, instead of being number of transistors we can put on a chip or in a certain area, this is actually number of instructions we can execute per microjoule. So this is a plot of energy efficiency. And if you compare, say, ENIAC to a 2009 laptop, there's been a factor of about 1 trillion improvement in energy efficiency. And that is what is enabling these far field, low power applications that I'm going to show you. It's also kind of interesting to note that there's quite a bit of room for improvement. If you think of the brain as an example, estimates of its energy efficiency put it out here, several more orders of magnitude beyond where our digital computing is today. This doesn't mean that we don't get brains until 2040, which sometimes is what people interpret this to be. It just means that our technology will not be as energy efficient as brains until then. Now, this is a related plot. The upper trace here, I took microprocessors and microcontrollers and plotted their energy efficiency in the same units, instructions per microjoule. And then the bottom trace is, if you think about a particular workload that we're going to execute using one of these microcontrollers, like let's say make a sensor measurement, encode the data, maybe compute a CRC, and then something like that. And then you ask, well, what's the total energy it takes to do that workload? And we assume we can transmit a certain amount of power wirelessly. So, the law allows us to transmit a certain amount. That power falls off as 1 over r squared with distance. So what that means is that if I pick a particular workload and I assume that I'm going to be able to execute it on increasingly efficient hardware, that means the range at which I'll be able to execute that workload is going up exponentially too. But because of the 1 over r squared fall off, the slope of this range scaling curve is 1/2 of the energy efficiency curve. So this explains why, 10 or 15 years ago, people were able to start making far field UHF RFID tags. Before that, the energy efficiency wasn't there to do this. But the more exciting thing about it is it means that the various things that we can do at fairly short range today, like 5 to 10 feet, if this energy efficiency scaling trend continues, we'll be able to do it longer and longer range. And so I think that will take some of the things I'm going to show you from being kind of interesting novelties to being something that is very practical, that you could really use in a variety of applications. So the first system that I'm going to describe is called WISP, which stands for Wireless Identification and Sensing Platform. And this is basically a UHF RFID tag that we created from scratch. So typically the way RFID works is there's a reader that emits, well, in this case, 915 megahertz RF carrier. The tag rectifies that RF energy and uses it to power some digital logic. The way the tag communicates back to the reader, instead of having its own radio transmitter, oscillator, all that stuff, it uses a technique called backscatter, where it simply changes the reflection coefficient of this antenna. So it has a little transistor that it shorts to short the two branches of the antenna together, or it can choose not to short them. And that generates a reflection of the reader's signal. So an analogy would be the reader's kind of like a flashlight, and the tag is sort of like a mirror. And by moving the mirror, you can affect how much light gets reflected back. So rather than having to have your own ability to create light, the tag just does this backscatter, which is, as you can imagine, it's very energy efficient because it's not generating any RF signals, it's just reflecting them. So the WISP has a microcontroller which can actually execute general purpose programs. We can also put sensors on it. And so it functions the same way as an RFID tag in the sense that it's wirelessly powered and it uses very efficient backscatter communication. But other than that, it's a lot more capable. So what I'm going to show you in this video is an early WISP. So this over here is a RFID reader. It's been dressed up to look like a picture frame. And in my hand is a 3-axis accelerometer WISP. So I'll play the movie here. I'm working the remote control with my other hand, which is why I look very strange there. So now as I tilt this stack of boards back and forth, the accelerometer is seeing gravity showing up on the 3 different channels, the X, Y, and Z channel of the accelerometer. The microcontroller is reading the values, the analog voltages that are coming out of that accelerometer. It's encoding them, computing a CRC, and doing this backscatter communication to encode the tilt for the reader, which is then drawing this picture. So you can think of this as a kind of like an input device. And in fact, this accelerometer is the same thing that's in the Wii game controller. Again, the key kind of interesting thing about this is that there's no battery in that stack of boards. And the other thing I should emphasize, sometimes people look at this and they think it's some kind of antenna polarization trick or something like that. It's nothing like that. That's a system that's being powered by the RF, and it's digitally communicating via backscatter. So in terms of what's inside that, here's a block diagram. So many of the blocks here are the same as what you'd find in a conventional RFID tag. The difference is the stuff on the right. So working in from the left, there's an antenna, some impedance matching, power harvesting circuitry that turns the RF from the reader into usable DC voltage. There's a regulator, voltage regulator. Whoops, I keep hitting that. And then these 2 components at the top and bottom are also something you'd find in a conventional RFID tag. Demodulator extracts data from the reader. So the reader is not always on. It actually modulates its amplitude in order to encode downlink data from the reader to the tag. And then the modulator is simply a transistor that is used to short the antenna, as I was describing before. So these blocks over here on the right are the pieces that are unique to the WISP. So there's a microcontroller with ADC and then external sensors. And the state machine, instead of being implemented in discrete dedicated logic, is actually software. And that means we can program it, which has a lot of exciting possibilities. So here's a view in a little more detail of the blocks inside the WISP. So here's the rectifier that we were using at that time, the demodulator, and some power management. And I'll talk just a little bit about each of those blocks. So this is actually a simulation of a one-stage rectifier. And in this visualization, color corresponds to voltage and dot velocity is current. So it's kind of nice that you can see them both separately. So over here would be the input signal from the antenna. So you can see these dots are just going back and forth. So it's a AC or RF signal. And then if you look at the dots on the diodes, say look at the bottom diode, you can see that the dots are only going up. So that's of course what the diode does. It only allows current to pass in one direction. And if you kind of look at it, you can see it's behaving sort of like a check valve or something like that, where again the current only flows one direction. And so driving it with an AC signal at this point in this configuration causes a DC output up here. So if you look at the dots up here, they're only going one direction because of the rectifying action of the diodes. Okay, and then in this simulation, we've sort of ganged 3 of those stages together, and what that gives us is voltage gain. So this point here where I'm putting the mouse is in this simulation is giving us 26 volts of DC. In this point here, after the second stage, we're getting something like 52 volts of DC, and after the third stage, we're getting 78 volts. So these component values obviously aren't specific to RFID, but this gives you the idea. And the reason it's important to get some voltage gain is that even if we have sufficient power to do the job that we want to do, if we don't have enough voltage, the electronics, the microcontroller won't turn on at all. So often, range is constrained by voltage, and so that's why we're interested in ways to boost voltage. This shows the rectification efficiency as a function of input power. So you can see it peaks here at about 32 or 3%, something like this, for that particular rectifier. Now this shows kind of the behavior of the power management block, which is sort of interesting. So the red trace is the harvested voltage. So starting from 0, this thing is waking up. And then these 2 lines up here are 2 thresholds that we have set. So there's a supervisor, which is just a piece of hardware that detects a certain voltage and then generates an interrupt when that threshold is exceeded. So the microcontroller sleeps until this upper threshold has been exceeded. Once there's enough voltage, the microcontroller wakes up, does its sensing, does its communication. That causes it to, of course, spend energy, which decreases the available voltage. And it'll keep doing that until it gets to this lower threshold. When it hits that lower threshold, it'll go to sleep and start charging back up again, which is this upward trace. Now, if the tag were further from the reader, there'd be less RF energy coming in. So this upward slope would become shallower. So it would take longer to get back to the charged up state. And then because the tag is obeying the RFID protocol and so forth, it's going to spend energy at basically the same rate. So the downward slopes here are always going to be about the same. But what you'll see is this simple mechanism of having these 2 thresholds has the net effect of causing the tag to delay in proportion to the power available. And so on average, the power expended by the tag ends up being exactly the same as the power available. So it's just a very simple mechanism that kind of has nice properties. Now, one of the things a lot of people are working on now is more sophisticated schemes that use software because the size of the job that you're executing can affect the way you want to do this duty cycling. If I have some job that takes longer to execute than the amount of time I have available here, then I may not be able to finish before the tag goes to sleep. So various ways of doing adaptive thresholds is something that many of my colleagues are interested in now. Okay, so we built the WISP, the very first WISP in, say, the accelerometer that I showed you. I think that was actually 2006. We hardened it quite a bit further than what you saw in that video, and then we made it available to academic collaborators through a program we called the WISP Challenge. So people could propose applications. We would send them some WISPs, and I'll show you some of the applications people have done. So this one was kind of a surprising one. This was with some neutrino physicists in Italy. They're working on an underwater neutrino telescope that's going to be 1 kilometer on a side under the Mediterranean Sea. It consists of 10,000 glass spheres, which you can see here, that have photomultiplier tubes inside them. So what they're looking for is when a neutrino comes through the water, it generates a flash of light, and they want to detect the sequence of flashes and then figure out where the neutrinos came from. Now their thought is as long as they're going to all the trouble to deploy these 10,000 glass spheres under the sea, they might as well try to do some oceanography as well. So they took the WISP and they potted it on the outside of the sphere. Then they put a small RFID reader inside the sphere and found that they could successfully make temperature measurements that way. So in this case, the benefit to them was not that they wanted to sense at long range, but they had this boundary, which is the glass sphere, that is not easy to breach. So they can't just add additional ports in this thing because that'll cause failures and it's expensive to create completely new housings like this. Plus each port that you have is further risk. So this is actually one of the examples of boundary integrity, where the key benefit of wireless power in this case is just getting through this 1 centimeter of glass, which is there's a high pressure gradient across it, and so you don't want to have additional ports in that glass. Now here's a completely different application. My student, a Lanson sample, realized that it's possible to add buttons to RFID tags, essentially capacitive buttons, using the same antenna, using the antenna for the RF purposes, but also for the capacitive sensing. So what you see down here is the signal applied to the antenna in the case that you're not touching it. And then when you touch it, you increase the capacitance. So the microcontroller is charging and discharging in a certain pattern, where if you add to the capacitance by touching it, it takes longer to charge and discharge. So this gets stretched out. But you can see that these are the RF functions. They're still unimpaired. So the neat thing about this is that you can imagine taking an RFID chip that still just has 2 wires, two ports, but starting to add user interface to it. So here's one button, but you can imagine doing a more sophisticated version of this that would be a keypad. So for things like credit card, you could have a PIN that you enter, and it would all be implemented just using the basic RFID capabilities. Here's another, this is a more recent application. So this is measuring EEG using the WISP. So Artem here created an EEG circuit that he interfaced to the WISP. So again, this is wirelessly powered and read, and there are now input devices, gaming systems that work, that use EEG. None of them are wirelessly powered at the moment. Now, one of the challenges we discovered when we did this is that the reader is emitting this large RF signal, and it's modulating it. The very sensitive voltage measurements that you're making here for the EEG tend to pick up the reader. So in this case right now, you multiplex between the sensing and the communication. But I think this is an interesting challenge for the future. The RFID protocols were designed just for this tag communication application. They weren't designed for sensing. So it's interesting to think about, can we redesign the entire protocol so that we can do sensing, communication, power simultaneously. It's interesting to think about how these different functions trade off with one another. Now, here was a completely different application of the WISP that took us by surprise. When we built the WISP, we thought it was all about sensing. But my colleague Kevin Fu is very interested in security and cryptography, and it turns out there's a whole community of people working on RFID cryptography for things like payment transactions and things like that. And in the past, there had, before the WISP, there had never been a way to actually implement applications and write code that would run an RFID tag, because they were just black boxes. So working with Kevin, we implemented the RC5 encryption algorithm on the WISP. And so that's interesting, first because we were able to just write software to do something on a tag. Also, the conventional wisdom had been that because RFID tags are so power constrained, you need special low power cryptography. But most of those low power cryptographic schemes were broken. And here we just used a conventional, full strength crypto system. And I think, if you look at the energy efficiency scaling that I showed at the beginning, that's part of the reason why, this makes more and more sense as time goes on. And people have gone on to implement many other crypto systems using the WISP. In fact, here's another example. So Intel commercialized the WISP design for an application in Brazil called Cineav, which is basically a tolling system, a kind of augmented tolling system. So in many places you have these tags that you put in your windshield that are essentially RFID tags that are used to pay tolls. Well, in Brazil they want to use that sort of system for many other things as well. They want to use it for buying gas. So you drive into the gas station and you're just billed for the gas that you use. Or you go into the parking lot and the payment happens that way. So to make that happen, they wanted a lot more security than the conventional RFID offered. So their standard calls for using the AES, the Advanced Encryption Standard. And so for us, we were able to just write some software, run it on the tag, and then we had an AES compliant system. The other people working on this, the other competitors, had to design digital logic, and it took a long time. So our team was able to get to market a lot faster because of this software approach. So another sort of application that my student Yves Zhao has been working on recently is doing ultrasonic localization implemented on the WISPs. So localization is a problem that people in RFID have been interested in for a long time because given RF propagation, it's difficult to localize RFID tags. It's difficult to find out where exactly the tag is because of the strange ways that RF propagation changes when someone comes into the room or a door opens or closes, things like that. It's hard to use the RF signals themselves to precisely localize something. So here the idea is to combine ultrasonic localization with RF. So the idea is that the RFID reader now will emit some ultrasound. The tags have ultrasound detectors. The RF signal tells all the tags to start their timers, and the RF propagation is practically instantaneous. But it takes a long time for the ultrasound to get there, because RF propagates at 1 nanosecond per foot, whereas acoustic signals propagate at 1 millisecond per foot. So each tag sits there waiting for the ultrasound pulse to come in, measures when the ultrasound arrives, and then transmits that data back to the reader using backscatter, and then the reader can localize the tags that way. So that mechanism of dual RF ultrasound had been proposed before, for example, by the Crickets and MIT project. But the nice thing here is that this is battery free and also integrates with RFID infrastructure, so that if you have some kind of tracking system and readers, you could potentially use this fairly easily. Okay, now here's a very new project. This is going to be coming out at the UBAComp conference in September. So the board that you see on the right we call the NFC WISP. So this is NFC's near field communication. And this is a standard that's being built into many phones now. So some Android phones have this, for example. So essentially the phone is an NFC reader. So this is 13 megahertz or HF rather than UHF. But so this board here can receive power from the phone and transmit data bidirectionally. Oops. So what we've done over here is we've integrated the NFC WISP with an e-ink display. So now you can take your phone, put it up to this display thing, shake the phone. The phone powers the NFC WISP with display, sends, in this case, an image of the screen, so captures a screenshot, which gets written onto the e-ink display. And because e-ink is bistable, once you've set each pixel black or white, they stay without any further power. So the bistable display is kind of a nice match to wireless power when you may or may not have power available. When you have the power, you set the display, then the power goes away, and the display changes. So there are probably many other applications for things like this. You can imagine having something on your door, which is a kind of e-ink sign that you could interact with your phone. Maybe it would also have a far field UHF RFID interface, so you could set an appointment or a note on the right on this display on the door, and then it would also propagate to the rest of the building and calendar systems and things like that. So I think this is going to be an interesting set of things to do. And I also wanted to highlight this because this is the first example I've showed so far of a display that is wirelessly powered. Now, all the WISPs that I showed you so far, the most recent one was we called it the WISP 4.0. A little advertisement, we're coming out with the WISP 5.0, which will have longer range and more memory and so forth. And we're going to do a similar project, a similar program to the WISP Challenge. In fact, my colleague David Weatherall and I just got a $1 million NSF grant through the, let's see, what's it called? Computing Research Infrastructure Program to make these and readers available to the research community. So that's something that hopefully by the end of the summer we'll have available. Okay, so now, whoops, I'm going to talk about another recent project where we wanted to go to much higher data rates for a wirelessly powered sensor system. So what I showed you with that first WISP video was an accelerometer that was being measured maybe 20 or 30 times a second. What I'm going to show you here is a way to do audio, which is much higher data rate sensing, but all using far field, battery-free sensing. And so for inspiration here, we're going back to something called the Great Seal Bug, which probably some of you know the story of. This device was invented probably by the inventor Leon Theremin, who was kidnapped from the United States, taken back to Russia, forced to work on bugs. It seems like this is the bug or one of the bugs that he came up with. So some Soviet Boy Scout equivalents gave this Great Seal of the United States to the American ambassador. They measured it, didn't seem to be emitting any RF signals, didn't have any batteries, so they thought it was okay. So he hung it in his office for 7 years, and it turned out that it was a bug the whole time. And the way that it worked was actually a version of backscatter. So the audio in the room would cause this diaphragm to vibrate, some kind of metallized membrane, and that would change the reflection coefficient of this antenna. So a truck would be parked outside the antenna, the embassy, broadcasting microwave, RF in. And based on the sound in the room, the amount of RF reflected would change. So the audio in the room was essentially modulating the backscattered RF. And so that's basically what led to backscatter communication as I was showing you earlier. So in the conventional WISP, we have a transistor that's used to short the two branches of the antenna together. So we're just doing binary, two levels of backscatter. But what we're proposing here, or what we've done here, is to take a conventional WISP, then add a microphone and an analog switch in series with the mic. So now we can talk to the WISP in the conventional way. It has a unique ID. We can send it a command to enable the microphone, in which case it closes this switch, and now the microphone is going to be directly connected to the antenna. And so it's going to go into an analog backscatter mode where it's actually backscattering audio in the same way that this Great Seal Bug did. So what you see in the blue up here, this part is the digital communication, digital traffic between the tag and reader. And then when it goes into analog backscatter mode, you see this trace here. So this is actually audio that is being backscattered. And now I'm going to play you two samples. The first was from a distance of 0.7 meters. So the microphone and the WISP is here. The reader is less than a meter away. Oops, sorry. Okay, here comes the audio.
Now here's something we hope you'll really like.
Sorry, that was too loud. Anybody recognize that? Rocky and Bullwinkle. Now here it is from 7 meters away. Whoops. So a lot more noise, and sounds like an AM radio because it is, AM modulation. But I think that, the thing that's exciting about this is now we have a microphone that has no batteries that we can read from, fair distance away. And so that's a much more demanding sensing challenge than what I showed you earlier with the 20 samples per second sensing. And there's obviously a lot of room for improvement with that, but I think it's an exciting result. Okay, so everything I've showed you so far was example of WISP, and in all those systems we were deliberately transmitting the RF power. So we had a reader whose purpose was to put out the RF power we were going to use. But it turns out that using similar rectification techniques, we can capture power from ambient sources like TV or cell phones. So we call this project Wireless Ambient Radio Power. And the image you see on the left this is a TV tower in Seattle, which puts out a megawatt of RF energy. And then this is a commercial wideband TV antenna. UHF is the band that we're using. And we're using essentially the same rectifier that was used in the WISP. And in this example, we're just powering a commercial off-the-shelf kitchen thermometer. So that was a first just proof of concept. The map that you see on the right shows the location of that 1 megawatt tower. And the inner circle is the range at which you'd expect to be able to get about 100 microwatts. And then this further circle, you'd expect to be able to get 25 microwatts. And the image you see up here is a newer harvester using just a dipole antenna. So rather than this large wideband antenna, this antenna is tuned to one particular frequency. I think it's like 739 megahertz, something like that. But it's obviously a lot smaller than the broadband antenna. So more recently, we've been able to harvest from cell phone towers. So the map over here on the right is the University of Washington campus. So there's a large fountain here. And on top of this building, there's a cell phone tower, array of antennas. At these green locations, we were able to harvest power from those cell phone base stations, do a sensor measurement, and transmit data short distance using like a Zigbee-like radio. And then at these two locations, the red locations, it didn't work, which my theory is it's maybe some sort of a multipath, bounce off this water, but we haven't investigated that yet. So in this case, the range is a lot less than with TV. Here we're looking at 200 meters, something like that. But sometimes people ask, well, is TV going to go away? Broadcast TV, maybe it will. I don't think cell phone signals are ever going to go away. But I think the density will increase and increase. So this is maybe not quite enough power to do everything that you want. Well, clearly it's not quite enough to do everything that you want now, but if cells get smaller and smaller and more numerous, this may become increasingly practical as a way to power electronics. Now, the way that we were able to operate using the cell phone power actually required a new type of harvester. So this is our old harvester. I showed you a simulation of something like this a few minutes ago. You can see it's just a bunch of diodes, Schottky diodes in this case. What we found is that when the signals get very small, corresponding to being very far away from the reader, you do better having just a single stage of rectification followed by a DC to DC converter to get the voltage gain. And so that allowed us, this new design allowed us to go from -9 dBm sensitivity, or corresponding to 125 microwatts as the minimum that you would need to operate. That allowed us to move to -18 dBm sensitivity, which corresponds to something like 15 microwatts, or in terms of range, that's 3x range improvement. So again, just to emphasize the various constraints, power in some sense is not really a constraint, because the tag can sleep for as long as it wants, in principle, to accumulate enough energy to do the thing it needs to do. So if you're willing to adjust duty cycle as much as you want, you can always, in principle, match your power required to power available. On the other hand, voltage is more of a hard constraint. If you don't have enough voltage, the thing won't turn on at all, and no matter how long you're willing to wait, the thing won't operate. So it's important to be able to get the voltage gain that you need. On the other hand, one of the nice things about the voltage constraint is that voltage is not a conserved quantity. So this box is actually generating more voltage than you're providing to it. So that's one of the kind of engineering opportunities is to find ways to get voltage gain when you need it. Now this plot here in the middle shows that the horizontal axis is basically range in meters. So this is 10 kilometers, 20 kilometers. The blue is the old harvester design, and the green is the new harvester design. So you can see that the old design basically stops working altogether at about 10 kilometers, whereas this new design with the DC to DC converter will work well beyond 20 kilometers. The other thing is at short range, the old design is actually better. And so one of the things we're working on now is trying to come up with a design that will win both at high power, relatively high power, and low power. Okay, so the next project I'm going to show you is a collaboration with my colleague Sham Golakota at University of Washington and our students. Now, one of the ways I like to think about this is, I described the WISP project, which used backscatter communication, and we talked about warp, which is ambient RF power, so powering things off ambient RF signals. This is sort of putting those two things together. So we have these devices, these ABC devices, that are powered by the signals from the TV tower. Then they communicate with each other by backscattering the signals from the TV tower. So just as the WISP did to talk to the reader, this tag over here has a transistor it can use to short the two branches of this antenna together. And it turns out that when it does that, this nearby tag can actually detect a change in the incoming signal, which I've plotted here. Now this doesn't work at very long range. These two tags have to be quite near each other, like less than an antenna length away from one another. But it's really kind of exciting that you can do this, because what it means is you have these tags that have no particular infrastructure other than some ambient RF. These things can be powered perpetually, continuously, and they can communicate with each other, even though you didn't have to deploy any infrastructure. So from kind of a user's point of view, it's almost like being able to have an RFID system, but with no RFID reader. The only reader essentially is the TV tower. Now you would have to, of course, one big difference is now all the communication has to be multi-hop, and you'd probably need some sort of a gateway to collect messages from the other units and then send them somewhere else. But it's an exciting new capability. Now we've done a couple of sort of demonstration applications here. We built these capacitive buttons onto this one, and there are a couple of LEDs on here. So the first application we implemented was kind of a payment type application. So let's say each one of these is a card with maybe some stored value, and I want to transfer some of that value from one card to another. I swipe the finger across. It backscatters a message to the other one. If it's received correctly, and this one we just have it checking a CRC. If it's received correctly, it flashes one of its other LEDs. Now, of course, that LED is very small, and it's only on for a very short period of time because we don't have a lot of energy, but it is something you can see. And the other thing is, of course, the update rate is low, so the LED can flash once every 5-6 seconds, something like that. So we've done this outdoors on the balcony at our lab, where you have a decent view of the TV tower, and we've experimented with the communication performance. So the horizontal axis in this plot here is distance between the units. So you can see it ranges from half a foot up to about 3 feet. This vertical axis is the bit error rate, and then the three colored plots are different data rates. So the red is 100 bits per second, the green is 1 kilobit per second, and the blue is 10 kilobits per second. So you can see that if we're willing to go as slowly as 100 bits per second, we can get a couple of feet away and have a very, very low error rate. If we're going to start going faster, like 10 kilobits per second, we're going to have a higher error rate, unless we're very, very close, like half a foot. So another application we've explored is, imagine something like books, which are all kind of uniform, books in a library, let's say. Each could have a tag like this. and the tags can talk to each other. So in principle, a system like this could figure out where every book is. Each book would tell its neighbor where it is. If one is off, that could be detected, or you could just pass the messages and figure out where everything is. So it's not clear exactly where this is going, but it's a really exciting and different way of doing things, because we have these units that potentially can last forever, can be completely built into something else, and really don't need a lot of infrastructure to be able to function. So if you step back and think about all of these things that I've showed you so far, what I think is exciting about it is that we've demonstrated that we can do RF-powered, battery-free versions of many of the components of various kinds of ubiquitous computing systems that you might be interested in. So I've showed you environmental sensing, for example, in the temperature sensing in the NEMO project. Several different input devices. So we did accelerometer, touch sensing, EEG, and microphones. Showed you a couple of cryptography examples. I showed you one location system, the ultrasound WISP. One display, although that was HF, so it's a little bit different. And then just now with the ABC system, I showed you peer-to-peer communication, which you could think of as kind of readerless RFID. But in aggregate, if you step back and look at all of these things, we have many of the pieces of kind of ubiquitous or even mobile computing systems that are now starting to be possible to be RF powered with no batteries. So I think it's going to be exciting to start putting these capabilities together into complete working systems. So that basically concludes the far field portion of the talk. And now I'm going to tell you about the near field high power system. Let me just do a time check. So are we going till 5:30?
5:30.
Okay.
Or technically till 8 in the morning, but
Oh, okay. We'll be here all night. Okay, so
cameras do go off though.
the next system I'm going to describe is called Wireless Resonant Energy Link, which we pronounce whirl. Apologies for the pronunciation there. So this was the first whirl system that we got working. This is a Lanson, and well, you'll see as he puts down this 60-watt light bulb, you'll see it being lit up from about 3 feet away from the transmit coil and back there, and that's about 75% efficiency, coil to coil. So now I'll explain a little bit about how that works. So the coils on the transmit side are represented here. So it's several turns of copper, and that has some inductance and some capacitance. It has a resonant frequency determined by those two values. The receive side also is a tuned circuit, tuned to the same frequency. And as it happens, we inductively couple into those, which isn't too important for our purposes. But if you work out the whole transfer function for the system, you get this kind of messy expression. And in a minute, I'm going to show you a plot of that is going to make it much more intuitive. Key point is we can figure out how this thing behaves. And now I'm going to show you a mechanical analog for this that will give you some intuition into how it works. So this is a simulation of the mass and spring system you see up here. So the transmit coil is analogous to a single mass and a spring, which has a certain natural frequency determined by the mass and the spring constant, just the way the LC circuit is determined by the L and C values. The receive side is also another mass and spring. And then the magnetic field that couples those things together that we're actually using to transfer the power is like this spring here. Now it turns out when you have a system like this with two coupled resonators, instead of having one resonant frequency, there are actually two resonant frequencies, or two normal modes. So this plot, what you're seeing simulated here is the in-phase mode, where the two masses are moving together. And then now I'm switching it to the anti-phase mode, where they're always opposite. And those two modes are both resonant frequencies at which the system absorbs energy very efficiently. and the frequencies of those two modes are different from one another. And it turns out that the tighter I make this spring in the center, the greater the splitting, which means the greater the difference in frequency between the in-phase mode and the antiphase mode. And so now I'm going to show you a plot of that transfer function. This is it right here. So the vertical axis is efficiency. This left axis here is distance between the transmit coil and receive coil. And then this axis over here is frequency. So at very short distances, we have a large degree of splitting. So when the transmitter and receiver are close to each other, that corresponds to a very tight spring in the mechanical analog. And now if you pick a distance, like let's say 10 centimeters, and trace across here, you can see we're going to hit one peak first, which is the in-phase mode. And then we're going to hit another peak over here, which is the antiphase mode. And so this surface is sort of the key to how this wireless power system works. So the key observation is that if we had a control system that could pick the frequency as the distance changed, then we could stay on top of this ridge. So even as the transmitter and receiver move back and forth from one another, we're going to adjust the frequency to stay on top of that ridge. And what that means is that we're going to get relatively constant efficiency. So if I were viewing this V-shaped plateau from the side, it looks fairly flat on top. So the key idea here is that as the transmit and receive move with respect to one another, either in distance or orientation turns out to work as well, we're going to adjust the system properties to keep the efficiency basically constant. And the thing that surprised me about this at first is that, when I had thought about wireless power systems in the past, I always just kind of assumed that the further away the receiver is, the less power you get. But what this shows is that in this regime, inside this red box, if the control system is working correctly, then we actually get constant efficiency even as the geometry changes. And so now I'm going to show you a movie. The first section of the movie we don't have auto-tuning on, and then in the next section you'll see auto-tuning enabled. So what you notice is the light is on at some particular distance. This is with no auto-tuning. When it's either too far or too close from the transmitter, the light is off. So back in terms of that plot, we were going right up the middle and over the top. Now we're turning on auto-tuning, so now the transmitter is changing its frequency in response to what's going on, and you can see that the light basically stays on essentially all the time, even as we change the orientation and so forth. And here's one other kind of neat trick. This is range extension. So now the receiver's out of range, we put this other coil in the middle, and the power actually multi-hops across. So in terms of mechanical analog, now we have three masses coupled by springs. So they get more and more complicated. Well, it keeps going quite a ways. I mean, we've done 5 or 6 hops. You can also make it turn the corner, which is kind of interesting. And when you have multiple of these together, the dynamics can get very complicated. So sometimes something strange will happen where you'll move one coil a little bit and one of the other lights will go on, and then you move it back and a different one will go off. So it gets quite complicated when you start.
Doesn't it? So it doesn't become chaotic fairly quickly?
It's not chaotic. I mean, it's a system of n coupled resonators, and you can figure out the eigenfunctions and figure out what happens.
Pendulums become chaotic very quickly, and they're coupled oscillators.
Mm-hmm. Well, yeah, maybe there's some regime where you could make this chaotic.
Okay.
Yeah, although pendulums are nonlinear once you get beyond a certain height. I'm not sure if that's important to the chaos. Okay. Now, one question that comes up a lot, of course, is is this safe? And that's really a key question: is at what power level is this safe and legal? So we've been working with the ITIS Foundation in Switzerland, who are experts in modeling the interaction of RF signals with the human body. And they call it the virtual family, which is basically they took CAT scans of four people, different sizes and shapes, and then they annotated the electrical properties of all the organs in the body. Then they can take those models, stick them into their simulator, into an EM simulator, and calculate exactly how much heating would occur for different applied fields. So, here we did some simulations with the transmit coils in different configurations, and from this, from the initial work, it looks like something like 50 watts is safe. Now, obviously, for every specific situation, you'd have to look at, every specific application, you'd have to look at it more carefully and see if you satisfy the various regulations. But the reason you can go to such high power levels is because the transmitter is mostly generating a magnetic field, which basically doesn't interact with your body. When you have an electric field, the water molecules in your body are electrically polar, and they orient to the electric field. That's, of course, how a microwave oven heats up food or water. So to the extent you can have just a magnetic field, you're basically able to transfer power without interacting with the body. Of course, the changing magnetic field generates a secondary electric field, like eddy currents and so forth, and those are the things that ultimately limit the power level that you can go to. So now I'll tell you about some of the applications of this that we've been exploring. The board that you see on the right is just a kind of fun receiver board. So I showed you in the initial plot that there was both a coil and a loop. What you see here is the loop. The other side of the board has a coil, meaning several turns. So this board receives wireless power, and it has a USB connector here. That's actually the power out. So you can take this board, take any USB device, plug it into this thing, and power it. So let's see. Now here's another just sort of fun application where we have this message fan. It's a little hard to see in the video, but basically this motor is spinning around, and there are LEDs along the fan blades, and so we're turning them on. So of course inside that white box there's no battery. It's all being powered by the wireless power from the transmit coil there. So that one is just sort of fun. We're collaborating with Rob Wood at Harvard to try to wirelessly power their robo-bees. So that group is creating basically robotic bees using a new kind of mesoscale fabrication techniques. But if you look in their videos, there are always, at least so far, fine wires coming in that are providing the power to operate the bee. So we're trying to wirelessly power this. So at first it'll just be a simple system where we have a series of transmit coils. The bee always flies up, and it'll just fly parallel to those. Now obviously long term you need some sort of a far field system if you want the bee to be able to go long distances. But our next step is just to show that this can be done using the near field approach. Now another area where we're applying this is we have a center that is joint between the University of Washington, MIT, San Diego State University, and there's some other partners as well. But this is an NSF Engineering Research Center for sensory motor neural engineering, and I'm the thrust leader for communications and interface. So what we're trying to do here is wirelessly power a certain type of brain implant called electrocorticography. So there are several different ways of making brain measurements. Earlier I showed you EEG, electroencephalography, where you're measuring from outside the skull. So you don't get very good signals that way because the neural activity propagates through the skull and it gets kind of mixed up. ECOG is a system where you apply electrodes to the surface of the brain, and that gives you, of course, much better signal than you can get through the skull, but it's actually less invasive than individual neural spike measurement systems. So there are arrays of essentially needles that get inserted into the brain, and those give the best signals. They can measure the activity of individual neurons, but obviously it's more invasive to actually stick a needle into the brain. So ECOG is something that's, there's quite a bit of expertise at University of Washington, and right now it's mostly used for patients who have, tremors and Parkinson's and things like that, or, seizures, various types. So today it's used on a fairly short-term basis for diagnosis. So a patient will come into the hospital, they'll put in an ECOG system, leave it there for a week or two, they'll find out where the seizures are occurring and make a treatment plan based on that. But the thought is that if you could completely implant an ECOG system, then potentially you could put these in and leave them there basically permanently, which could be used for these therapeutic purposes, but also potentially for brain control, brain control interfaces and things like that. So in this application, we're very size constrained because the goal is to put the whole thing inside the skull. So we have to do a chip for this. So working with my colleague Brian Otis, we're designing an ECOG chip that can be wirelessly powered using our HF wireless power system. Now this is the most exciting application actually of our wireless power. On the right is a picture of my collaborator, Dr. Pramod Bondi. He's a heart surgeon at Yale School of Medicine. And on the left, you see a heart pump called the left ventricular assist device. So this is an alternative to a total artificial heart, where instead of taking out the old diseased heart, you put in a pump in parallel with the heart. So the old heart is still there doing what it can, but now you have this mechanical assist. Now when you put a pump in parallel with the heart, that consumes a lot of energy. It takes something like between 5 watts and 30 watts to power that pump. So there's really no possibility of battery powering this the way you can battery power a pacemaker or defibrillator. So today there's actually a cord that protrudes from the abdomen that brings the power and control signals into this pump. And as you can imagine, that gets infected, and that seems like is really limiting how much LVADs can be used. So there are something like 500,000 cases of heart failure. There are about 2,000 LVADs implanted a year, also only about 2,000 transplants a year. So there's potentially a lot of opportunity if you could solve the infection problem to have LVADs become a much more widely used therapy. So that's what we're trying to do, is eliminate the transcutaneous drive line. So in this, here's one visualization over here on the right of how this could work. So the patient would have a receive coil implanted under the skin, the controller for the motor and the motor, as well as the RF rectification circuitry would all be implanted. Then outside there'd be a transmit coil, which could be worn in a vest, along with some batteries. And then kind of what we'd really like to do longer term is have a transmit coil that could go in certain key pieces of furniture, such as a bed. And then maybe the vest wouldn't be needed while you're sleeping. Obviously to go out and so forth, you'd still need the vest. And in this application, we think it's going to be necessary to have an implanted battery as well that would provide maybe half an hour of operation so that the patient could shower, change the vest, etc. So this shows kind of many of the pieces that are in the system that we've built for the heart application. I think I won't talk through all the details of this one. Okay, in this video I'm going to show you, this is my student Ben Waters with a wearable portable transmitter. So this would be analogous to the vest that I just showed you. So that's the transmit coil. Sometimes he's not a suicide bomber. Now he's going to pull out a receive coil, and you can see it coming on. People usually say Iron Man when they see this thing. You can see it's it's approximately it's the distance that you would need. For some reason he didn't want to have that coil implanted inside him, so we did the demo with it outside. Oops, whoa. Okay. So we did implant this in a couple of pigs, which I won't leave up for very long. But so we've done some initial experiments which show the full system does work, and that was successful. So that basically concludes the description of wirelessly powered systems that we've worked on. So we talked about first far-field systems. So there's WISP, which is a system in which we're transmitting power deliberately. Then we talked about warp, which is another far-field system, but there it's using ambient RF. And we talked about ambient backscatter communication, where we sort of combine those two ideas and have tags that can communicate with each other using just ambient RF signals. And then I showed you the near-field systems. So whirl is our name for the high-power wireless system, and Freed is what we call the application to heart pumps. So overall, when I step back and think of what are the implications of all of this, I think one exciting possibility is that we may be able to have zero power communication of certain types. So for example, your phone may be completely dead, but it may be possible to still send an SMS using power that you've harvested from ambient RF. And I also showed you the analog backscatter, where we were actually collecting audio using ambient RF as the power. So maybe it may be possible to even transmit some voice this way. So overall, I think it's increasingly feasible to run mobile ubiquitous computing systems using ambient RF power. And as time goes on, given the energy scaling that I showed you earlier, I think these things are going to become more and more practical, more and more compelling. I'm going to put up a little advertisement for a book that I have edited. It has a collection of papers on many of these topics, both by my group and by other collaborators. Also, there's a new journal from Cambridge University Press coming out on wireless power transfer, so I encourage you to submit to that if you're interested. Now, I have some robotics work that I also do, but I think given that we're almost out of time, I don't know, should I talk about a little bit of that? Or
We'll go until we turn off the camera, then we'll do cool stuff.
Okay.
Then you pass out the gold bars.
Sounds good. I better be here in person for the gold bars. All right. So, robotics is one of the application areas that I'm very interested in for sensor systems. So far, what I've been talking about is this problem of powering sensors, which is a very important problem. But here I'm going to look at some new sensors designed for specific applications of robotics. Now, to back up, the video I'm showing you here is what I worked on for my PhD thesis. So there's an array of electric field measurements, and it's measuring my hand, the way my hands interact with the electric field, and we're inferring what the hand position and orientation for both hands is from that. So that led to kind of a surprising technology transfer where Honda ended up creating a car seat sensor using this sensing mechanism to disable passenger side airbag firing. So now every Honda that's been made since about 2000, 2001 has our sensor in it. And if your head is near the airbag, the side airbag, it's disabled using that sensing technique. But in robotics, I've taken it a couple of different directions. So in this application, I'm going to show you a robot that is sensing power, sensing the 60 hertz electric field emissions from the outlet. So you can think of this as a robot that's kind of finding its own food. Of course, its food is electricity. So every outlet has a 60 hertz emission that it generates. So we took the ground plug of the robot, instrumented it with a sensor, and as it was scanning back and forth there, it was looking for the peaks in the 60 hertz and then aligning to plug in. Now in this example, this is really taking the exact same sensing technique that I showed you for the hand sensing, but now we're building the sensors into the robot hand instead of going the other way. So this is inspired by several species of fish sense their environments this way. They generate an electric field and look at how things change. And what you're going to see in this video, the first part, we're measuring between the palm. There's a transmitter in the palm and receiver in the fingertips. And so each of the fingertips has this sensor. And so by balancing those sensor values, you can align the hand with the object. And then once it's aligned, it switches into another mode where it's using a transmitter kind of in the back of the finger that's sensing on a shorter range to align with the apple. And finally, the other thing you'll see in this video is that we can tell whether I'm touching the object or not, because when I touch it, I ground it. And so the sensor can distinguish that. And you'll hear some beeps that indicate whether the person is touching the object or not. This is using the long-range sensors. And once the signals get stable, it switches into the
Bounded.
Finger sensing mode.
Thanks.
That beeping is it detecting whether you're touching it. So it waits for Lewis.
There you go.
That beep was it detecting him touching it, and it releases once he's touched it. Okay. Now that sensing mechanism turned out to be pretty nice, and I'll show you another really fun application of it in a minute. But one problem that we had with that, or one shortcoming, was that it depends on the electrical properties of the material. And so it works for many materials, but things that are like a thin plastic case, it doesn't work for. So we wanted to come up with another pre-touch sensing mechanism that would respond to a different set of materials. So I call this seashell effect pre-touch. And here the idea is when you take a seashell and put it up to your ear, you hear the sound of the sea. Of course, that's not really the sea. What it is that the cavity has properties. It filters the ambient sound in the room. And as you get it closer and further from your head, the properties of that filter change. So we're going to do the same thing. We take a pipe instead of a seashell, put a microphone in it. And as that pipe approaches an object, the way the pipe filters the sound in the room change. So we have a reference microphone that's not in the pipe. We have another microphone in the pipe. And then we're going to build that whole thing into a robot finger. So here's our PR2 robot. These are the pipes that I was describing with the microphones. And this shows, as a function of distance, the frequency that we observe. So you can see, with standard deviation and everything. So you can very reliably use this as a sensor to detect whether you're close to an object or not. And so we've used that for various applications. In this first section of the video, you're going to see a pressure sensor, very compliant object. The pressure sensor is not able to detect the paper because it has some minimum force that it can sense. Now here we're using the pre-touch sensor, which can detect the paper, without touching it. So you can think of that as sort of a force sensor that has no lower limit on what it can detect. And then here's a more complicated application where we start with a point cloud collected by the Kinect. That's these little red dots here. Then we're going to use the pre-touch sensor to augment the point cloud. Here we go. So we infer some other points there. Fortunately, I'm not going to have time to explain this really properly, but we guess about the existence of some other points, then we plan a grasp. And if the points we want to use for grasping are uncertain, meaning we didn't actually observe them, we just guessed that there was something there, then we're going to use the pre-touch to fill in those points. And so we just filled in some points that were detected with the pre-touch sensor. Then we replan the grasp using those new points. And if the process converges, then eventually we get to a point where the points we want to grasp we're sure have something there, and we go ahead and do the grasp. So eventually the idea is to combine the grasping procedure with this pre-touch sensing so that it just happens as all part of one process. All right, so finally I'm going to show you a video where we were able to kind of demonstrate this in a kind of high visibility, fun setting. So this is similar to what I showed you with the apple.
Documented from one of our research laboratories.
So that's Craig Barrett, Governor Schwarzenegger, and Chancellor Merkel of Germany. So shaking hands with the robot here. Says it's his drinking hand, so he's glad he's not squeezing any harder. And now, what I learned in this was that Chancellor Merkel has a PhD in physics, and she's actually about to do an experiment, unplanned experiment on stage.
Electric field pre-touch that right now is used to track this orange. Bring it over to
So that beeping is the same thing you heard before. It's detecting whether you're touching the object. So when he touches it, the beep happens, it releases. Okay, so this is the ribbon to launch CBIT. And now watch Chancellor Merkel's little experiment. She touches that ball, and you heard the beeping. That was it detecting the fact that she touched it. But fortunately, it was no longer programmed to release at that point. So if it had done the same thing it was doing with the orange, it would have let go in front of thousands of people. The ribbon would have dropped, and it would have been very embarrassing. But so that was one where the demo gods smiled on us. So if you imagine putting all of this together, I showed you various wirelessly powered sensors, implanted sensors. You can imagine having wisp-like brain sensors that are used to pick up motor commands from a paralyzed person. The kinds of pre-touch sensors I just showed you in a prosthetic arm. Maybe that arm is wirelessly recharged. So I think it's exciting to imagine what you could do putting all of this together. And with our Neural Engineering Center, we're actually trying to do many of these things. So that's it. Thank you very much for your attention. Are kind of benefiting from different things. So one of them is cord elimination. So here's a mess of cords that you see. Obviously, wireless data can help eliminate quite a few cords, but it may not eliminate all of them. Of course, one way to eliminate the power cord, at least some of the time, is to use batteries. So battery elimination is another potential benefit of wireless power that works in some applications. And if you think about, well, what are the benefits of getting rid of batteries more specifically, one is your device can potentially be, have a perpetual lifetime. If it's getting the RF kind of live, then you may be able to eliminate the battery altogether and not worry about it dying. If you can eliminate the battery, you can reduce the size often. So sometimes we're in a volume constrained situation. And of course, you can get rid of weight as well. And you'll see some applications today where the weight constraint is really the benefit of wireless power, or removing the weight constraint. Now this is one where I'm not sure I have the best description of it, but the two images you see here are images of the monolith from 2001: A Space Odyssey. So one way to think about this benefit is, imagine you have, future version of the iPhone. Here's an existing iPhone. It has quite a few connectors and buttons and things, but you can imagine if you have wireless power and wireless data, and if we sense buttons using some kind of capacitive RF sensing technique, then you could imagine making something like a phone that's just a completely sealed monolithic box that has no ports or no features whatsoever. And actually you'll see several applications today where what you might call boundary integrity is the key benefit. So it's not just for consumer electronics, but if you start thinking about biomedical applications, that's a case where you don't want extra ports being put in your body, and we'll see some other examples of that too. Finally, here's I've got Emperor Palpatine from Star Wars helping us out here for this one. I was talking to some NASA people about the possibility of transferring power wirelessly between spacecraft, and so there the benefit is non-contact energy transfer. So, if you have these spacecraft that can be sent off accidentally with small amounts of force, then the fact that you don't have to use force to make and break connections is potentially a nice benefit. So these things are all similar and related, but as we go, I'll point out when we're taking advantage of these different benefits. Now, when I think about the space of wirelessly powered systems, this is one of the ways I like to carve it up. So I have one axis which is far field versus near field. Far field literally means further away, probably in terms of RF more than a wavelength away. And I also have some near field work. And the far field systems tend to be smaller amounts of power, longer range. The near field systems are larger amounts of power, shorter range. And the other axis that I use is you could call it wild or planted. And that is, is this power that we deliberately transmitted with the intention of collecting again later? Or is this power that was already out there for some reason that we found and used? And that's what I'm calling wild. So each of these, we've explored several of these boxes, and these are the names of the systems that occupy each box. And as we go, I'll talk about the specifics. So one final sort of piece of introduction is, if you think about the far field systems, the thing that has made these possible is energy efficiency scaling. So if you look at this plot, not very carefully, it looks like kind of a Moore's law plot that you've probably seen many times. The horizontal axis has time in decades, but in this case, the vertical axis, instead of being number of transistors we can put on a chip or in a certain area, this is actually number of instructions we can execute per microjoule. So this is a plot of energy efficiency. And if you compare, say, ENIAC to a 2009 laptop, there's been a factor of about 1 trillion improvement in energy efficiency. And that is what is enabling these far field, low power applications that I'm going to show you. It's also kind of interesting to note that there's quite a bit of room for improvement. If you think of the brain as an example, estimates of its energy efficiency put it out here, several more orders of magnitude beyond where our digital computing is today. This doesn't mean that we don't get brains until 2040, which sometimes is what people interpret this to be. It just means that our technology will not be as energy efficient as brains until then. Now, this is a related plot. The upper trace here, I took microprocessors and microcontrollers and plotted their energy efficiency in the same units, instructions per microjoule. And then the bottom trace is, if you think about a particular workload that we're going to execute using one of these microcontrollers, like, let's say, make a sensor measurement, encode the data, maybe compute a CRC, and then something like that. And then you ask, well, what's the total energy it takes to do that workload? And we assume we can transmit a certain amount of power wirelessly. So, the law allows us to transmit a certain amount. That power falls off as 1 over r squared with distance. So what that means is that if I pick a particular workload and I assume that I'm going to be able to execute it on increasingly efficient hardware, that means the range at which I'll be able to execute that workload is going up exponentially too. But because of the 1 over r squared fall off, the slope of this range scaling curve is 1/2 of the energy efficiency curve. So this explains why, 10 or 15 years ago, people were able to start making far field UHF RFID tags. Before that, the energy efficiency wasn't there to do this. But the more exciting thing about it is it means that the various things that we can do at fairly short range today, like 5 to 10 feet, if this energy efficiency scaling trend continues, we'll be able to do it longer and longer range. And so I think that will take some of the things I'm going to show you from being kind of interesting novelties to being something that is very practical, that you could really use in a variety of applications. So the first system that I'm going to describe is called WISP, which stands for Wireless Identification and Sensing Platform. And this is basically a UHF RFID tag that we created from scratch. So typically the way RFID works is there's a reader that emits, in this case, 915 megahertz RF carrier. The tag rectifies that RF energy and uses it to power some digital logic. The way the tag communicates back to the reader, instead of having its own radio transmitter, oscillator, all that stuff, it uses a technique called backscatter, where it simply changes the reflection coefficient of this antenna. So it has a little transistor that it shorts to short the two branches of the antenna together, or it can choose not to short them. And that generates a reflection of the reader's signal. So an analogy would be the reader's kind of like a flashlight, and the tag is sort of like a mirror. And by moving the mirror, you can affect how much light gets reflected back. So rather than having to have your own ability to create light, the tag just does this backscatter, which is, as you can imagine, it's very energy efficient because it's not generating any RF signals, it's just reflecting them. So the WISP has a microcontroller which can actually execute general purpose programs. We can also put sensors on it. And so it functions the same way as an RFID tag in the sense that it's wirelessly powered and it uses very efficient backscatter communication. But other than that, it's a lot more capable. So what I'm going to show you in this video is an early WISP. So this over here is a RFID reader. It's been dressed up to look like a picture frame. And in my hand is a 3-axis accelerometer WISP. So I'll play the movie here. I'm working the remote control with my other hand, which is why I look very strange there. So now as I tilt this stack of boards back and forth, the accelerometer is seeing gravity showing up on the 3 different channels, the X, Y, and Z channel of the accelerometer. The microcontroller is reading the values, the analog voltages that are coming out of that accelerometer. It's encoding them, computing a CRC, and doing this backscatter communication to encode the tilt for the reader, which is then drawing this picture. So you can think of this as a kind of like an input device. And in fact, this accelerometer is the same thing that's in the Wii game controller. Again, the key kind of interesting thing about this is that there's no battery in that stack of boards. And the other thing I should emphasize, sometimes people look at this and they think it's some kind of antenna polarization trick or something like that. It's nothing like that. That's a system that's being powered by the RF, and it's digitally communicating via backscatter. So in terms of what's inside that, here's a block diagram. So many of the blocks here are the same as what you'd find in a conventional RFID tag. The difference is the stuff on the right. So working in from the left, there's an antenna, some impedance matching, power. Thanks very much for that introduction, and thanks for having me today. So the title of my talk is Wireless Power Transfer and RF Energy Harvesting, New Options for System Designers. So I am going to be talking about ambient RF as indicated, and I'll also be talking about some other RF power transfer schemes. Let's see. Now the reason I call it New Options for System Designers is not because I'm going to be talking very much about design, but one of the things I think is most important and interesting about wireless power is the different design options that it will create. So before I get started, I'd just like to acknowledge my graduate students and alumni. This is Alancin Sample, who was my first PhD student. He graduated about a month after I started at UW because we'd been working together at Intel for about 5 years before that. So I thought if I could only crank out one PhD student a month, I'd really have something going. So far it's slowed down, unfortunately. Now before I get into the meat of the talk, I'll just give you a little overview of my group. I call the group Sensor Systems. And from the name you might think that that's all about inventing new sensors, and we do some of that, which is what I have labeled down here at the bottom. But we're also interested in all the other things around that that it takes, that you need to take an isolated sensor and turn it into a usable system. So that involves communicating with sensors. And most of what I'm going to be talking about today is actually about powering sensor and actuator systems. We're also interested in various applications of sensor systems. So things like ubiquitous computing, medical applications, robotics, and I'll actually talk about some of each of those. But the bulk of the talk today is going to be about our work in wireless power. Whoops, the B key. And I will unpack these acronyms as we go. These are several different systems that we've developed. So before I talk about some of the specific systems, why wireless power? I mean, in some ways it seems so obvious that you don't even need to motivate it, but it's kind of interesting to think about what are the specific benefits, partially because different applications